Hello, welcome to my channel. Today I'm going to look at mechanics of solid, in particular elongation of a rectangular bar. So I've been given a question. This is my tapered bar. It is increasing in thickness. Then I've been given the value of Young's modulus 210, denoted by E. Compressive force, axial force 20 kilonewtons. So that force is this denoted by P. Then a constant width of 30 millimeters. So when I'm talking about the width, I'm referring from this distance to this point, denoted by B, which is similar from this point to this point. So that has the symbol B. Then the thickness varies from 20 millimeters to 40 millimeters. So that means the smaller side has a thickness of 20 millimeters, the larger side has a thickness of 40 millimeters. So for that, I'm going to denote this side with a capital T. Then for the smaller side, I'm going to use a small t. So I'm told, derive an expression for change in length, thus solve it. So that is what we are going to do. We are going to cover today. Just a minute. All right. So let us start. I'm going to start by considering a small element from this point to at a distance of x. So at my point x, I'm going to draw a region, and I'm going to shade it. It has a thickness of dx. All right. So I'm going to consider this small region. So in this small region, I'm going to give it an extension delta. So the extension delta denoted by that triangle, and it has a length of dx. So we know that strain is given by change in length all over original length. So the change in length is the extension delta divided by original length of dx. That is going to form my equation 1. Secondly, I'm now going to consider the whole body. So for the whole body, I'm going to use this formula. We know that strain is given by stress all over Young's modulus. Then stress is given by force all over area. So that is going to be P all over area A. P represents the force that is experienced. That is my P. So I'm going to substitute this into this formula, and I shall have stress is given by load all over area multiplied by Young's modulus E. So I'm going to consider that formula for the whole body. Now, the strain at a distance x from this point to this point is going to be given by the load divided by the area at a distance x multiplied by the Young's modulus. But we do not have the value for ax. We have the value of p, the value of the Young's modulus, but we don't have for the area. Now, to get area x, the area of x, area is given by width multiplied by thickness. Now, the width for the body is from this point to this point. It is similar, so that is going to be b. The thickness, this region varies from small t to capital T. So I'm going to consider the thickness from this point to this point, and I'm going to represent it by Tx. So it is going to be given by B multiplied by Tx. So how do I get the value of Tx? So to get Tx, we are going to apply some geometry. And I'm going to consider the triangle ABC. So that is going to be my triangle A, B, and C. Alright. Then I have this shaded region. I'm going to represent it by a straight line, and I'm going to name it G and F. So we can represent this in form of ratio, whereby AF divided by AC is equals to GF divided by BC. GF divided by BC. Alright, so AF, in the diagram, AF is from this point to this point. It has the length of X. Then AC is from this point to this point, and it has the length of L. That is the length L. So AF, that is X all over AC from this point to this point all over L is equals to GF. So to get GF, it is from this point to this dotted line. How am I going to get the distance GF? Now, from this point to this point of the tapered region, it has a thickness of Tx, and this point has a thickness of T. So I'm going to take Tx, I subtract T, and I'm left with that of this point and that point. And because it is symmetrical, I'm going to divide it by 2. So Tx minus T divided by 2. So Tx minus T divided by 2. Then I'm going to divide that by the region BC, from here to here, capital T, from here to here, small t. So the same, this capital T subtract the small t. I'm left with that for that part and that part. Then it is symmetrical, so I'm going to divide by 2. So divided by capital T minus small t all over 2. So let me erase at this point. So x over L is equals to Tx minus T divided by, the 2's are going to cancel out each other, so I'm going to be left with capital T minus small t. Alright, so let me also rub here. So at that point I have XL, but what we want is the thickness Tx. So I'm going to make Tx the subject of my formula, and that is going to give me Tx is equals to X all over L into bracket T minus T plus T. So I have my Tx. So the area of region AX is given by B multiplied by Tx, that is B multiplied by X over L, T minus T plus T. Alright, so that is the area AX. So having that, we go back to my formula. I had the strain of X is given by P all over AX of E. That was for the whole region. Then for the smaller region, I had EX is equals to delta all over dx. So the two equations are similar. What I'm going to do, I'm going to equate the two of them. So P all over AXE is equals to delta all over dx. So I'm going to make delta the subject of my formula, and I shall have delta is equals to p all over axe multiplied by dx. So that is now what I'm going to consider. So the delta p axe dx, that is the extension of a small element. So to get the total extension or elongation for the whole body, I'm going to sum up this small extension. So how do I do that? I'm going to integrate this to find the sum of those small extensions. Therefore, the total extension, I represent it by TE, is going to be given by integration from the limits, at this point is 0, for the whole length, capital L, then P all over AX. Now for AX, I'm going to input the value that I had. Recall we said that AX is B into bracket X over L T minus T plus T. So that was the value of AX. Now I'm going to input it here at this point. So I shall have E, then B into brackets X over L T minus T plus T, then the dx. Don't forget dx. Okay. So I'm going to rewrite this in the form of, now at this point, the load P, Young's modulus E, and the width B are constant values. They do not change within the body. So I can write them in front of the integration sign, and I shall have P over EB integrate from L0, then, so dx is going to be my numerator, divided by, I shall have, now for this point I'm going to write it in the form of T plus T minus T all over Lx. So there's a reason why I've written it that way, and this is why. To integrate this is a complex number. So from our SMPs, the maths table, we have the formula integration of dx a plus bx is going to be given by 1 all over b ln of a plus bx. So in this case, this is my a, bx, a plus bx. So to integrate that, I shall have p all over eb multiplied by 1 over b. So that is going to be L all over T minus T, the ln of A plus bx. So that is the denominator. Let me write it this way, into bracket T plus T minus T all over L. Then I input my limits from 0 to L. From 0 to L. Okay, so I have made it simpler. So now I'm going to input the values of my limits. Sorry, I forgot an x at that point. I'm going to input the values of my limit at this point x. Now, let me create some space. So I want us to evaluate this part. So just forget this part for a moment. Let us evaluate this part. So once I input L, I shall have ln into bracket t plus t minus t L all over L subtract the ln of t plus t minus t 0 all over L. Alright, so that L cancels out with that L. Then anything multiplied by 0 is 0. So that cancels out to 0. Then inside the brackets, I can open up the brackets. I shall have t minus t. So t minus t is going to cancel out. And I'm going to be left with ln of t subtract. At this point, the whole of this part was 0. So minus ln of t. So I input this back to my formula. And I shall have p all over EB multiplied by L over T minus T, then input this ln of T all over T. So basically I've replaced the minus sign with division for logarithms. So I shall have that. So good. Now this is the formula for finding the total extension, and I believe we have answered the first part of the question. So secondly, we are going to solve it. So what you're going to do is to just input the values. So the value of P is 20 kilonewtons. So that is 20 to power a third divided by A is 210 giganewtons. So 210 to the power of 9 multiplied by the constant width B, 30 millimeters, expressed in SI units. So that is 0.03 meters, multiplied by the length. At this point, I had my length 250 millimeters. So in meters, that is going to be 0.25 meters. So 0.25 divided by T minus T. So the capital one is 40 millimeters, the small one is 20 millimeters. Conversion 0.04, 0.02. So over 0.04 minus 0.02 multiplied by the ln of 0.04 all over 0.02. Please don't get confused by that part. This is separate, 0.03. Do not combine the two. So once you evaluate, I believe you are going to get an answer of 2.751 times 10 negative 5. Then this is extension, so it is in the form of meters. So that is going to be our answer. So we have solved the part for deriving the expression, and also we have our answer. Thank you so much for watching the video. If there are any comments, kindly comment below and tell me the various parts you'd like me to tackle. Thank you.